Hi guys, I have a new device in front of me at the table. I cannot tell you what brand it is because I cannot read Chinese, but the only thing I can tell you, it is a battery charger. And this charger was made especially for a 48 volts lithium iron phosphate pack. So 16S configuration. The voltage is fixed, but the speciality of this charger is you can adjust the amperage at the output, and that is very nice. You can set any value between 5 and 25 amps, so anybody could use this. If you have a small battery pack or a large one, you can just manually set what you need. But this device I did not buy as a standard charger. I already have 3 chargers which are fixed output at my power wall. You know that already. I have a special idea what I want to do with this one. This charger only makes sense for me if I can somehow automatically set the output of this charger. And this is what we are going to try. We are going to hack this charger and control it via a microcontroller, and then later on this will be done, this task, by my controller in the power wall. See, we have a knob here. This does not necessarily tell us what kind of component is sitting in the back of this. There are a few different ones which could be hidden behind this. I will show you in a moment what those options are. But at the end we are going to unscrew this side here and look behind, take some measurements, and then we can continue with our research. So today's video is all about researching this device, and then later on we are going to implement this, if successful, into the power wall. There's sort of 3 different scenarios which kind of component is hidden behind the knob. The number 1 would be a so-called rheostat. That's simply a variable resistor. So you have typically 2 pins, and 1 pin is going via a slider, and the resistor will change its value. So resistance here is the important thing which is changing and needs to be then processed. The second option is a quite classic one. It's a so-called potentiometer. We have now 3 pins. Between the 2 outer pins, it's a high and low pin. There the full value of the resistance of the potentiometer would be found there. And then we have a 3rd pin, that's as well a slider. And usually a potentiometer is actually a sort of voltage divider. So the outgoing voltage on the slider is typically what needs to be processed. So if you have the outer pins on ground and VCC, then the voltage on the slider will vary when you move the slider. So while the 2 first options have been analog components, the 3rd one is a digital one and is called a rotary encoder. So you also have a knob, you can turn it clockwise or counterclockwise, and this will lead to different digital signals, and those signals can be then processed. You will need a microcontroller for that, and then you just tell by software what shall happen if the knob turns right or turns left. Let's unscrew this. It's only 4 screws here, and this should open already. This side plate is just connecting to a aluminium heatsink. And here we are already. This is simple component hidden here. It looks like a potentiometer, and it also has a stop end at the low and the high. So this looks like a potentiometer. It is connected nicely here inside with a GST XH 3-pin connector. So that would tell me also maybe a potentiometer. Let's just measure what kind of values we have here, because we need to know, of course, which value this component also has, right? Okay, so we are on resistance measurement. So let's see if I take the two outer pins from this connector. So this would be high and low. What do we read here? About 10 kilo ohms. Let's measure only two of these here. Okay, so midpoint, that would be slider, and I think that's the high end. So if I turn up, okay, the kilo ohms are going up. So yes, when I go up, it's 10 kilo ohms. Going down, it's gonna be 0. Yeah, this is a classic potentiometer. Now we know that we are dealing with a standard 10K potentiometer. What can we now do to replace this manual component and make it work with a microcontroller? And this I have here already on my breadboard. So here you see a microcontroller. This is a Arduino Nano, which I use because it's very breadboard friendly. And then I have a component here, and this one is a so-called digital potentiometer. This also, of course, needs to be the same value as inside the device. So this is, luckily I ordered a 10K digital potentiometer. So it is called a X9C and then 103. 103 means 10 kilo ohms. Let's compare the previous measurements on the charger to measurements here on the digital potentiometer. How does a digital potentiometer actually work? There's a series of 100 resistors inside that small chip. And by telling the slider to which position it should go, you will get a resistance at the slider. So we have a choice to name a position between 0 and 99 on that chip. So the position 49, for example, should be then equal resistance between slider and high or low position. Measure the outer pins first. Okay, high to low, and we have 10.2 kilo ohms, which is good. I will now reset the microcontroller again. So the sketch is doing nothing than counting up the values. So let's take the slider and the high end, and you see we are starting from a high resistance and getting smaller and smaller. So yes, very nice. This works. Now I want to take this, set up the charger at the Powerball, and we are going to see if this also works under real life conditions. Yeah, I'm here at my Powerball, and as you can see, there's a new door here. This is door number 4, and let's open it and see what's inside. Voila, as I told you, I'm building a new second electronics compartment. There's already my new inverter. It is inverter number 3, a Sun 2000, and it will serve the third phase here on our property. I started to connect everything, but it's not yet done. What we're interested in for our test today is here is an extension of my battery bus. We're going to connect the charger here at the battery bus, and then we're going to try to charge the battery with it. I have now connected the DC to my 48 volts bus here, and there's already one LED coming on. It stands for intelligent, so this came on via the connection of the DC, otherwise the device is turned off. So what we're going to do first is just test it via the manual knob and then see how it will do when we connect the digital potentiometer. Let's switch the charger on and click, and yeah, here already I can see the reading of amps. By the way, you can change the display to be voltage or amps, so let's put it back on voltage, and you can see 51 volts. Put it back on amps, so we see 1 amp. That seems to be just a display because it's not charging yet. So let's crank it up a little bit. 2 amps, 4 amps. Aha, but now it's already starting. So 4 amps and the machine is going into charge. 5 amps, 6, 7. Let's go up to the top. And 25 amps. So the charger is working. Set it down to 1 amp and see when it will cut out. 4 amps, 3 amps, so still charging at 3 amps also, 2 amps, and now fan is off, 1 amp, and charging is off. So 5 amps to 25 does not seem to be correct. It seems to be really somewhere to start charging maybe around 3-4 amps, and it will then continue if you go down also maybe. Okay, let's turn it off and then connect the digital potentiometer. Okay, I have now connected the digital potentiometer to the charger and running the charger via it. And I have to confess, this is not the first try. The reason why not and why it actually did not run very well at the first tries is because I did not know how the connector inside the charger and the digital potentiometer pins have to be set up. And it took me a while to find the exact configuration, and there was also one more thing to do at the digital potentiometer. I had to connect a common ground. So I will show you the configuration after this test, but now it works. So the sketch is again the charger, the potentiometer is increasing its value, and you can see here at the amp meter of the charger it is counting slowly up. So I am increasing every second, I'm increasing the value by 1. So it takes about 4 seconds for 1 amp to increase on the charger. And you see now we have 12, 13 amps now, so the value is just rising. I have my serial monitor here on the laptop, and it says we should be already at 20 amps. We are on a value of 85 at the moment. So this is telling me, of course, that this now is not linear yet. So the value of the amps and the value of the potentiometer does not correspond at the moment. But this is no problem. Now the value is 99, so it should be maximum. Now we have 24 amps shown on the charger. So what I want to find out now is just which exact potentiometer value is corresponding to which amperage which is coming out of the charger. For this I simply have now a piece of paper. I wrote some amps there, and now I'm going to restart the cycle again and then write down the potentiometer value at the corresponding amp. And this will then be used in the main sketch of the power controller. So important, it works, and I will soon just know how to program the controller to get out what I want. This is how it finally turned out to be at the test. On this side I have my amp values on the charger and which of the potty setting this will equal to. So you can see 4 amps is position 14, 6 amps 25. So at the low end it requires 11 steps for 2 amps. This is getting smaller and smaller, the difference, and here at the top we have 22 amps corresponds to 95, while 24 amps is 99. So you can see it's not linear when controlling via the potentiometer. So in the final sketch of the Powerwall controller I can of course say, okay, I want to set, let's say, 14 amps, so I will send the value of 70 to the potentiometer and that will be okay. So, and this is what I was talking about, charger connector versus potentiometer, how it has to be connected. So at the charger, this is looking into the charger, and when we look at that 3-pin connector, we have VCC, we have voltage of the slider and ground to the right, and these need to be connected to the X9C potentiometer, which have here a VL, then VW and VH. So the VL goes to the ground of the charger and also needs to be connected to the ground of the potentiometer. So this connection does not exist. It will be later on done on my adapter board. And then we have VW, that's the slider going to the slider, also at the charger of course, and the V of the high end has to go to the VCC of the charger, and that's already it. This is working perfectly fine. So now in future we can control this charger with a digital potentiometer. So I'm actually going to order now 2 boards. One, this one is a small adapter for this digital potentiometer. Why do I want the adapter there? I don't like to solder wires directly to breakout boards, stuff like that. I just want to have my GST XH connectors, put this into a small junction box as always. You know, sometimes you need a few extra components, like here a few pull-up resistors to define the signal a little bit better if you have long cables, etc., which you might have in my Powerwall. So that's why a small adapter for this. So at the end I will just plug in the board. And the second is the version 5 controller board. The reason why I need the other version is because now I need more relays, right? I have a 4th charger and a 3rd inverter, so the inverter needs to get soft start and the other relay is used then for the 4th charger. Yeah, this looks like this. There's a few other minor changes, a little bit more SMD components, etc. This is going now to the PCB manufacturer, and it will hopefully be here with me in about 2 to 3 weeks. Yeah, this was a day of research. The only thing I need to do now is to wait for my two boards. So the small adapter board for this breakout board, which will already set all those connections in the back, which requires to talk to the charger. And then my version 5 controller for the Powerwall, so that I have all those extra relays and the correct connection also for the digital potentiometer. Once I have all this here, we can then take this charger, mount it into that new electronics compartment, and then I will also write the sketch, the software for the Powerwall controller, and then we are going to finally have a much more precise way of removing excess energy from our solar system, which would else just leave our property for free. Once all this is done, next time we are going to take a detailed look how this will work, and hopefully you will like this approach of excess energy management. Okay, so thank you for watching this video. Please, if you have some comments, comment on the down, and yeah, like the video, subscribe to the channel if you haven't yet, and I see you next time.